Volumetric analysis. Key knowledge. Determine the concentration of an organic compound by volumetric analysis, including the principles of direct acid-base and redox titrations, excluding back titrations. So anything prior to this study design, 2016 and prior, has back titrations in them. So that's not assessed if you come across those questions. And so when we get to exam revision and we look at those previous study designs, I'll go through the exams and say, these are the questions that are relevant to this study design for you, okay? So I'll help you with that. Principles of volumetric analysis. Calculate concentration of a solutes, right, in moles per litre or grams per litre. List the characteristics of a primary standard. Give examples. Describe how a standard solution is prepared from a primary standard. Describe the steps in volumetric analysis. Distinguish the difference between endpoint and equivalence point. Identify equipment used in volumetric analysis. I'll pause it there and ask you some questions. Excellent. So let's go through it quickly then. Key terms: concentration, the amount of solute dissolved in a volume of solvent. What we do is we ignore the solute volume. So technically speaking, solute will take up some of the volume, but we ignore that, right? Grams per litre or in molarity, moles per litre. More often than not, we're looking at moles per litre rather than grams per litre. Standard solution, different to primary standard, okay? Standard solution is simply a solution with an accurately known concentration. A primary standard, note, it doesn't say solution. We don't have a primary standard solution. We've got a primary standard, we've got standard solutions, two separate things. So standard solution, accurately known concentration. Primary standard is a substance, pure in its form, that its amount in mole can be determined accurately from its mass. And there's like things about primary standards that we'll go into. Key equipment, as we've listed off just now: volumetric flasks, accurately known volume of glassware making standard solutions. That's what we use it for. Pipette, accurately delivered fixed volumes, yeah, to about the nearest 0.01 of a mil. They're very accurate pieces of equipment, and we can even calibrate them depending on the temperature and using distilled water. Yeah, we can using a really precise electronic balance, a pipette, and some distilled water, we can very accurately calibrate pipettes to probably the closest 0.001 of a mil. Yeah, they're very, very good pieces of equipment. What's great about titrations is you get really good data, unlike in the combustion prac that we did much earlier in the year, where you get terrible data because you lose so much heat to the environment. Volumetric analysis, you get excellent data. Yeah, we'll talk more about that. Conical flask, right, is where we put all of our samples into. Flask, broad base, narrow neck, we use that in titrations. Burette, that's the long bit. We can see them at the back of the classroom. It's got that little tap on them. Delivers variable volumes of solutions accurately. And an indicator. And we've got different indicators that we're going to look at as well. So we don't just use the same indicator each time. And we'll talk about, one of the things we'll talk about too is why in redox titrations we don't need an indicator, is something else to consider. Depending on the nature of the titration will change the appropriate indicator to use. So that often comes up in exams. Key concepts. Titration is the process. Yeah, that's the whole thing. The whole thing is called a titration. A titer, right, is the volume of liquid measured by the burette. Concordant results. This is a really important concept. Concordant results are titers that vary within narrowly specified limits, plus or minus 0.05 of a mil, or 0.1 mils from the lowest to the highest value. We're wanting 3 concordant results when doing titrations. So we may have to do 5 or 6 titrations in order to achieve 3 concordant results. Yeah, we are going to get some variability within our results. That's the nature of random errors, right? Natural variations within the results. But we repeat enough, right? We're going to minimize those variations and more accurately and precisely determine our results. Only the average titer should be calculated only from concordant results, not just all the results, okay? So try and shift our thinking. Average is not just all of them divided by the number of trials. Average is only adding those concordant results together and dividing by the number of those results that are concordant. And this strange word, an aliquot. Aliquot, I don't actually know how to pronounce that. I just say aliquot, right? An accurate volume of liquid measured by a pipette. Cool. Now, there's not one way to do a titration. Sometimes we put the standard solution into the conical flask and our unknown into the burette, and sometimes we do it the other way around. We put the standard into the burette and the unknown into the conical flask. Yeah, so as stated, equivalence point is what we're actually looking for, which is why we need to select the appropriate indicator, because we want the indicator to change color, or the end points, all right, the change in color of an indicator. So we want permanent is the key word there. So if it shifts back one way or the other, we know it hasn't quite reached that end point. We want to select an indicator such that the end point is as close to the equivalence point as possible. So equivalence point, it's the point of neutralization, or the point at which we reach those mole ratios within our chemical equation. Primary standard. Characteristics. They're highly pure. They're stable, which means they don't react very readily. They have low hygroscopicity. We've seen that before with biodiesel. They're hygroscopic. They absorb water from the environment. So sodium hydroxide is not a good primary standard because it absorbs water from the environment. If we're absorbing water from the environment, our mass is inflated. So if I was to try and make a primary standard using sodium hydroxide solid, the concentration would actually be slightly lower than the calculated concentration, because the amount of mass I'm adding, some of that mass would actually be water. That makes sense? Yeah? Cool. High molar mass. And if we have a high molar mass, right, our concentration calculations due to weighing errors or uncertainties in our electronic balance is minimized. So if we look at, again, sodium hydroxide has a molar mass of what? 23 plus 16 plus 1. So we've got molar mass of 40. You look at the difference between that and sodium carbonate, it's got a molar mass of 106, right? If we have a 0.1 gram difference in over 40, right, percentage-wise is much higher. So what's that, 2.5%, right? 0.1 over 106 is what? Under 0.1%. Tom? Non-toxic, readily and cheaply available. Some examples. Base anhydrous. What does that word mean? What does anhydrous mean? Without water, right? Sodium carbonate does absorb some water from the environment. So what we would do is we'd place it into an oven. It's very stable. It's got a high thermal threshold before it decays, right? So we can set it to 110 degrees, boil any residue of water off, and then we can use that as our primary standard. Acid, not one I would expect you to remember. Potassium hydrogen sialate, KHC8H4O4. Bit unusual, but so yeah, not one I would expect you to know. And to make a standard solution, or standard solution, I accurately weigh out a sample, let's say of my sodium carbonate. I would rinse this out, right? Rinse it, pour it through, rinse it, pour it through. And so what I'm doing is ensuring that I'm collecting as much of that primary standard as possible, minimizing any loss due to transfer. So it's one of the sources of error in any sort of analytical technique is loss by transfer. So we minimize that through lots and lots of rinsing. Rinse the flask, rinsing the sides of the bowl until such a point where we've got about half filled. Got a half filled volumetric flask. And then at that point in time, we want to ensure that all of that solid has dissolved. And then we continue to add more water till about 1 centimetre or 2 centimetres underneath this line here. You see a gradation or a often referred to as a calibration line on your volumetric flask, okay? And with that, that is the accurate known volume. So we want to go just below that, and then we'd use a dropping pipette to make up to that calibration line. And I'm not sure if you can see it accurately, and I can't zoom in on here, unfortunately. Is that, notice how the bottom of the meniscus sits on the calibration line. So that's what we're looking for, right? So to accurately or read my volume, so this includes reading off a burette, we're reading where the bottom of the meniscus sits. Drip that up, and then we're going to invert to ensure that the solution is homogeneous, right? Because if I make up the solution here and just add water, we end up with what's called a concentration gradient if that's not mixed thoroughly, right? So if I'm just adding water to this solution, the concentration at the bottom of the flask will actually be slightly higher than the concentration at the top of the flask, yeah? And if you've ever seen really well-made cocktails that have layers in them, that's a concentration gradient, yeah? According to densities of different like sugars and syrups. So we put, you know, the most sugary thing at the bottom because it's the highest density, and then the next layer and you add them too. But if you mix them all, you get the same concentration of sugar throughout your cocktail. That's what we want. We don't want the nice cocktail with the layers. We want it all mixed because it all tastes the same anyway. Okay, steps. We want a known volume aliquot of one solution of an unknown concentration using a pipette into a conical flask. Or, as I said, we'll put our standard into the pipette. So it's one or the other. Two ways of doing it. We put the other solution of known concentration, or vice versa, dispensed into the burette. There's actually some steps we do before we do this. Any guesses as to what we do before filling them up? No.
You rinse it out with the same stuff, the solution.
Yes, excellent. Yeah, and that comes up in exams as well. So I'm happy you brought that up. We rinse I say in titrations, we rinse it with what goes in it. Yeah? Pretty good, huh? We rinse it what goes in it. So whatever solution is going to go into the burette, we rinse it with that solution. Whatever solution goes into the pipette, we rinse with that solution. What do we rinse the volumetric and the conical flask with? Why? You don't know. Yes, you're correct. Why is the answer.
Which one accurate? Because you just add extra water at the end anyway.
Right, exactly. With volumetric flasks, we're adding more water anyway. So rinsing it with water doesn't change the number of mole of the substance we want going in it. Yeah? Measure the titer from burette from one endpoint once the endpoint has been reached. And we're looking for that point in time where it has just changed colour. If the colour is too intense of a change, it's called an overshoot, meaning that we've gone long past the endpoint. Repeat the titration, work out the average titer from the concordant result. Indicator must be added. Colour change called the endpoint. Want to select the most appropriate indicator. Pipette, we've spoken about that. Draw it up past the gradation line. We might use these or might use the bulbs, right? And then I like these better because I can't use the bulbs very well. I lift it off, I cap it with my thumb, gently twist it to allow some air in until such point, again, where that meniscus sits on, I'll move that camera out of the way, until that meniscus sits on that gradation line. So, burette, we can read in between the lowest intervals.